Good morning, everybody. Next week we'll hear from Professor Sequoia University, who claims to be developing the next search engine. And we have the opportunity to find out what's the status of the search engine development, and in particular, the controversy about limits. We have the pleasure of introducing Professor Rountree, and the Livermore National Laboratory. He's going to tell us why terabytes is only kilobyte. Welcome, our guest speakers.
Hi, so I'm Barry Rountree, Lawrence Livermore National Laboratory. First item of business, you've got Kim Cups coming later in this semester. Definitely go to her talk. I may drive down and catch it myself. She's really good. So I hope I don't steal too much from her thunder. She's also from Livermore. So starting off, I've been asked to consider recently, you all are computer scientists, that's what your degree says. Why are you getting this degree? So it's not a vocational degree as such, because if you wanted to learn to program, you could go off to a community college, take lots of Java classes, C++ classes, and you'd probably be better prepared to go off MBA coder. It's a reasonable preparation if you want to get a PhD in computer science. I didn't get my undergrad in computer science. Mine was in theater. And in theater, you tend to ask questions like, what is theater? And why am I here? In computer science, I'd like to frame this talk by saying my job title is computer scientist. I don't code, and my interns don't let me. As a computer scientist, I think it's like the analogy of doctor to medical researcher. If you are a programmer, you are looking at one program. I need to make this correct. I need to make this program run faster. If you are a doctor, you are looking at one patient. And you can draw from a lot of medical research, but you are still focused on the one patient. As a computer scientist, and I think there are a lot fewer jobs as computer scientists, I think they're more fun, you are looking at classes of programs and classes of machines, like a medical researcher is looking at a population of patients. So perhaps that's why you are getting this degree, to look at this field as, here is a class of Java programs, here is a class of applications. What are the security issues across the class instead of individual ones? What I'm going to be talking about today is a class of supercomputers. They aren't built yet. We're just trying to design them right now. The large problem is we want a machine that goes 1,000 times faster than the biggest machine on the planet right now, that only uses 3 times as much power. This is a whole different way of thinking about computing, but first, most of you probably haven't been exposed to supercomputing. Let me start off by showing you what it is that these machines do. We do physics simulations. We're a nuclear weapons lab. That's our primary bread and butter. We also do climate simulations. We do material science. If you've seen 18-wheelers with these funny fins going along the bottom, we helped with that design too. That's airflow, computational fluid dynamics. This simulation is just aluminum and copper, both at a very high temperature, going in different directions. What happens at the interface? And you can solve this problem on your laptop using a set of equations. The problem is your error bars are going to be huge. If you want to reduce your error bars, what you can do is model each individual molecule. There are 9 billion in this particular simulation. You can see how that really can't fit on your laptop. So what we do in supercomputing, and of course I can't draw this on here, but we take a bunch of these atoms and stick them on a particular compute node. The more compute nodes we have, the more atoms we can do, the finer scale we can get, the more true the actual simulation is. So here, things are starting up, and now you start getting these vortices, and that's what we're interested in for this particular simulation. Rather than do this as a set of equations, looking at it as a whole, we are going in and again simulating each of those individual molecules. That's what takes so much compute power. There's one other thing I want to point out with this. If I'm a compute node and I'm cranking away on the physics of my atoms, I can go forward a little bit in time, compute the physics, but eventually I need to talk to other processors near me and find out what is happening on the boundary. That is a huge that's a huge performance issue. If I have to go off processor, off my local memory, and talk, that slows me down a lot. This is what all of our simulations do. That's how we set them up. So, if Kim Cup shows you the same thing, act like you've never seen it before. That is a cartoon version of what the physicists at Livermore use these computers to do. So now let's go off to what I do. Real quick, just a bit of terminology. You know gigabytes. Tera is 1,000 times more than that. Peta, 1,000 times more than tera. The fastest machines on the planet we have now are petaflops. To give you an idea, this is 1.5 million processor cores all ganged together. We're already into a dozen, 15, 18 megawatts of electricity just to get this doing something useful. I'm going to be talking about power today. This is the instantaneous measurement. This is watts. That's how the light bulb is rated. Energy is power over time, kilowatt hours, joules. This is what I did for my dissertation. It turns out to be a much easier problem. I'm happy that the PhD students who have come after me get to work on the power problem. And an idea of cost, a megawatt year is a megabuck. We really don't have a dollar problem here. We're the government. If we need to build this, we go to Congress, we make our case, it gets built. What we have really is a political problem. If we wanted to scale up the machine that we have, it would be using gigawatts of electricity. Effectively, we would have to go out and build a mid-sized power plant to run one computer. This isn't going to happen. It may happen in China. They are set up a bit differently there. They've got, well, let's just leave it at that. What we want to do is get to an exaflop at 20 megawatts. This is a list that's generated every 6 months, the top 500 machines on the planet. You can see the one in China was recently the #1. Oak Ridge has the #2. We're in at #3 at the moment with the Sequoia machine. And let me zoom in a bit here. That machine's up to over 3 million cores. And how many teraflops you can run at. Theoretical peak is a lot higher than we can actually achieve, even with really stupid benchmarks. This is a problem. You've built a machine and you can't figure out how to write code that makes use of all of it. The power is what I'm mostly concerned with. We're already up to 17 and we have a long way to go to get this number up to 1,000. Now, eventually, the hardware folks are going to give us a machine that theoretically can do that many floating point operations in 20 megawatts. My problem is, how do we get useful science done out of that? A little bit more background. So, this is just a deeply weird disturbing, wonderful graph. Let me point out the y-axis is in flops. That is a log scale. If you don't know what a log scale means, make a note of it, ask someone later. Basically, you're going up by a factor of 10 every line. The blue line is how many flops the #1 machine on the planet was doing at this particular year. And this has just gone up and up and up and up. This is the number 500 machine. This line is the sum of the flops of the top 500 machine. The scary line, this is a slide from Jack Donguera, that's his laptop. His laptop is faster than the #1 machine back in 1993. This has been a huge explosion in computational power, and we have access to this. If you have an idea that needs this much computing power, talk to me. We may be able to get you on these machines. We're still trying to figure out how to make good use out of this. And we're expecting this will continue going up more or less in the same fashion. So if you come up with a problem that needs 100 times more computing power than we have now, just wait a few years. By the time you're done with your doctorate, that machine will be there. Okay? So this was a little optimistic. Back in 2010, we started thinking about what would this kind of exascale machine look like. And we were hoping that by 2018, we would have an exaflop machine. That's probably 2022 at this point. This machine is hard to think about. Basically, we're going to have some number of nodes, compute nodes. The fastest machine when I started doing this was the Blue Gene L. Each node is going to be a Blue Gene L machine. We'll probably have 1,000, 10,000 nodes. Looking at concurrency, right now your laptop probably has 2 or 4 hardware cores on it. Maybe your server, you get up to 16. We're looking at 1,000 hardware cores in this design or 10,000 cores in a different design. How do you write code that keeps 10,000 cores busy? If you get a bit of load imbalance and one core decides to take 20% longer, that's 20% of the time that the rest of the node is just hanging out doing nothing, burning electricity. We're going to have an interesting time with failure. If your mean time between failure is 50 years and you have 1 billion cores, a lot of cores are going to be failing a lot of the time. In fact, we've had early machines, due to some soldering issues, where we couldn't get 6 hours of runtime before the machine fell over. And we actually had to go in and fix that. Now we're scaling up 1,000 times bigger than that. How do we handle the failure? That's somebody else's problem. My problem is the megawatts there. So that's where we're going. To give you an idea of how we're getting there, this is the list of the top 500 machines. I'm just showing you 2007 and 2013. This does not show you how fast they run. This is just the top 500 as a class. And what you can see here is that you've got flops per watt, log scale. This is how efficient you are. The further out you go, the more efficient. Here is how many megawatts you have coming out of the wall. What this tells me is if you want your machine to be in the top 500, you can have a relatively inefficient machine and dump electricity into it, or you can have a really efficient machine and not put quite so much electricity into it, or if you're up here, you're doing both. But there's this really nice wavefront where if you are below this in terms of either efficiency or how much power you're buying, you're not in the top 500. As we go out a few years, that wavefront is still there. The blue dot is exascale. You can see that we're running out of power headroom a lot faster than we're gaining efficiency. That's going to be a problem. So, that is the big picture background. Now let's look at some data. This is a Blue Gene Q machine. These tend to be the fastest ones on the planet. It has a PowerPC processor in it that would not be out of place in your microwave. These are very, very low watt processors, and we buy a lot of them. This Vulcan, I don't even think we tried to get it into the top 500. It's not a huge machine, but it's sizable. What I've got here on the y-axis is megawatts. How much power is this machine drawing? On the x-axis, time, several months of use. What I'm measuring here is the total machine power draw. And this shape is really consistent across every supercomputer we stand up. We build it, we get it on the machine floor, we start running tests. There's a lovely application called LinPack. I believe it's dense linear algebra. We've got the life tuned out of LinPack. When you're running LinPack on one of these machines, you have the bus maxed out. You have your vector units maxed out. Your cache is being used really efficiently. You are striding through DRAM in a very predictable way. Basically, every part of your compute node is getting used close to where it is at peak. And you see, this machine was provisioned for 2.4 megawatts. We're right close to the top of what this machine can do. The problem is, nobody cares about LinPack. This is a great program for warming the machine up and seeing what dies, but it does not get us any scientific useful results. It's a toy benchmark at this point, at least for the physics that we do. Apologies to anybody who uses LinPack. So we get done testing this, we hand it over to the scientists, and we start doing actual physics on it. Actual physics is a lot harder. You start running into bottlenecks. You end up not using your vector units, which are power hogs, nearly as much. Maybe you are latency bound, and so a lot of the time your whole processor is hanging out, waiting for stuff to get in from memory. Your power drops, you're only using about 60–70% of your total power. If you are a programmer, I think you might look at this and go, okay, great. Or let's first scale this up. Same usage pattern, now we're looking at 20 megawatts. We've built a machine that says, okay, we can do an exaflop. And then as a programmer, you run your code, it's not hitting that power boundary, you're happy. If I as a computer scientist come to you though and say, look, we built the wrong machine. We provisioned this thing for 20 megawatts. You as a coder, you're not using all of the power I gave you. What's wrong? Make your program go faster and use more power. And you're probably going, well, how do I do that? This has already been optimized. If we end up building an exascale machine that looks like this, we have wasted a lot of money. What I want is a machine that looks like this. Power is the scarce resource here. If you're going to measure utilization from your scarce resource, then this machine is getting used at 100% of capacity. This machine has much lower utilization. I would hope the Department of Energy would call us up and say, what the hell are you doing? Why did we buy you this machine if you're not going to use all of it? As a programmer, I doubt that you've got a really good idea how to code to draw exactly 20 megawatts or 5 watts or any other amount of power. It's not something that we teach. It's not something we've had to worry about. You may have some idea about energy. If you're coding an app, you don't want to be running down your battery. So that's okay. But if you're doing that and you look at your power draw, your power is going to be all over the place. Your energy may be lower if you do this, but you have lots of power spikes. If you have power spikes at megawatts, you damage equipment. You don't want that. How we are going to get here is building a lot more compute nodes than we can run flat out at the same time. We then bring in our 20 megawatts, we distribute it differentially among all of these nodes, so we're always at that bound. And some compute nodes are running faster, some are slower. You total it all up, you have 20 megawatts. My big problem as a computer scientist, and we're getting actually money to study this, if you have that architecture, how do you run as fast as you can? How do you maximize the science you can get out of this machine? Nobody has looked at this problem before. We're breaking new ground here, and I've got a lot of good PhD students working on this, and a few undergrads too. And yes, I could stand a few more, that's a hint. So, that's where we want to go. We start trying to get there, and we run into some really strange problems. Starting with the Sandy Bridge processor out of Intel. You can dial in a power bound to the chip. So you can say, do not run at more than 60 watts. And what the processor does is it dithers the clock frequency several dozen times a second. It's measuring power. You give it a window, about a millisecond, 10 milliseconds. It guarantees that the average across this rolling window will be at or under your power bound. And they're getting pretty good at doing this. So, great. I can now control how much power my chip is consuming. The application developers don't have to worry about this. They don't want to think about power. So we do this, and something weird happens. When I can zoom in here? Yeah. When I do not run with a power bound on, my x-axis is time, my y-axis is power. I have very little variation in time. This is reassuring. If I run the same program on different processors that are ostensibly the same, it takes the same amount of time. This is a nice world to live in. There is a significant variation in the power draw each of those processors take to do this. Okay, so what? If I put a power bound on, I'm not making these processors any more efficient. So what happens is my variation in power falls over and turns into variation in time. If I have a power bound on, they all run at the same power. The power bound works. But, and if I get down here, I've got one processor that's 7% faster than my slowest processor. If you're doing this on laptops, who cares? If you have a tightly coupled physics program where I do some work and then I ask you, okay, what are your results? And then I go on, and you are taking 7% longer than me, I am gated to the speed of that least efficient processor. If I build a machine out of these processors, basically, if I get unlucky in the processors I'm assigned, I'm losing 7% performance right out of the gate. So we called up Intel and went, what are you selling us? And they went, yeah, we knew about that. It's like, well, so right away, just putting a flat power bound across all of the processors isn't going, well, it will work. It will kill performance. This is going to get worse in future generations, we're told, and we need to figure out a way of dealing with this. We've had extensive talks with Intel. It's not going away. We're trying to figure out how to manage it. All right. It gets worse. Don't try squinting on this yet. I'm going to be zooming in. That was one benchmark on about 64 processors. This was seen as a large problem, so I was able to get some machine time on 2,386 processors, run 2 benchmarks over, that's 4 power bounds. What I'm going to be showing you here is the average clock frequency on the y-axis and the speed up time on the x-axis. We're going to be doing 95 watts, 80, 65, and 30. So let's zoom in. MG is a multi-grid benchmark. It hammers memory pretty hard. We call this a memory-bound program. It likes to run at about 100 watts. If you put a 95 watt power bound on, you see you have this nice, well, it's not nice at all actually, but you have a distribution. Each of these points is a single processor running this program at that bound. And already just 5 watts lower, that might slow down anywhere from 3.3% to nothing at all. EP is an embarrassingly parallel benchmark. It just sits in the CPU and generates random numbers. Doesn't hit memory at all. It likes to run at about 90 watts. At 95 watts, it's not slowing down much. We have this population of processors here that seem to go 1% slower. Don't know why. Intel didn't know why either. There's a big variation in clock frequency, but that doesn't seem to affect the execution time. Basically, this is what we would consider normal. You're running at about the same amount of time across all of these processors because it is not running into its power bound yet. So let's put a tighter power bound on. These two are the data that I just showed you. I might as well explain this while I'm here. I have circled the 5 least efficient processors. I circle those same processors throughout the rest of these graphs. MG is keeping about the same shape. It's slowing down kind of predictably. Okay, I can think about MG. EP, on the other hand, got hammered. Because MG is memory bound, if I change the CPU clock frequency, it has less of an effect. It's mostly gated to the clock frequency on the bus. EP, its performance is totally dependent on what your CPU clock frequency is. So here, under a power bound, this can go anywhere from 8% slowdown to nothing at all. MG, you're going from 3% to 6%. That's fine. Let's keep going. 65 watt bound, EP has now blown past MG. Right? So, this processor is rated to go down to 51 watts. Had a bright PhD student, Usman Sarud, and I really wish I had thought of this first, but that's why I have bright PhD students. He said, well, let's put in a lower number and see what happens. So instead of going down to 51 watts, we went down to 30 watts and the wheels fall off. That little blob up there is all of the data that I've just shown you. What we're seeing is 200% slowdown to 300% slowdown to 400% slowdown. And the folks at Intel were really interested that this managed to run at all. What I find more interesting here is MG has now lapped EP. What this tells me is I don't have a nice linear relationship where I can just say, okay, tell me how memory bound you are, and I can plot a line and predict where you're going to be. There's some nonlinearity going here. That makes it that much more difficult for me to say, I have a job. I want to run this under this power bound. How long is this job going to take now? We don't know. That's one open problem. It gets worse. Let's just get rid of power bounds for the moment. Intel, going back to the Nehalem processor, has this idea of a turbo mode. If you have some thermal headroom in your processor, you're not anywhere close to melting it, and the processor feels like it, and you have turbo enabled, you can go up to higher clock frequencies than you can access as a user. This heats up the processor. Once it crosses a threshold, it drops down again. So basically you get this dithering again, and you end up Ideally, running faster, you use a bit more power. It's a pretty cool thing. If you are using more cores, you're generating more heat. You can't go as fast in turbo. The fewer cores you use, the faster you can go on average. Now, this is kind of deep in that usually if you are trying to optimize your code, you just use all of the cores. And maybe you don't run that much faster, but you don't expect that you would run any slower. On these processors, and this is the way of the world going forward, you now have to wonder, okay, if I use that extra core, does my clock frequency drop and I actually slow down? So, starting off MG, a larger version. Now I'm using 175 CAD nodes. There are 2 processors per node. I am using 8 up to 16 of those cores. And I'm balancing them out equally or as best I can on both processors. What I'm showing you here is the 8-core version, the 10-core version, the 12-core version. You've got speed up, time on the x-axis, you've got power on the y-axis. And these graphs are when you're having a good day as a computer scientist. Really easy story here. I use more cores, I go faster, I use more power, diminishing returns. What could be simpler? No, it's not that easy. If you use an odd number of cores, your performance tanks. Here's 12 cores, there's 13 cores. It's better to use 10 than 13. I don't know. Eventually, I'm going to stick an undergrad on this and figure it out, but I've been threatening that for the last 2 or 3 years and it hasn't gotten done. So don't do that, okay? This is almost certainly this benchmark specific, but we don't know why. It may be something on the motherboard with the processors communicating. We don't know. This so far has been baseline turbo is disabled. Now we're going to enable turbo, allow faster clock frequencies, and more power draw, okay? And that looks pretty reasonable. If you're over at 8 and you turn on turbo, you go a whole lot faster. And you use more power. If you're at 16, you go a little bit faster and use a whole lot more power. Now what's interesting here is that 12 is your optimal. How would you know this unless you went through and did every configuration? We would really like to have a model for this. We don't yet. You can go to 14 and 16. You're not running any faster, but you're burning a whole lot more power. Now, if you've got 10,000 compute nodes and you make this mistake, that's a whole lot of power you're burning up to no good effect. You could have given that to somebody else to use, and we could have gotten more science done. That's why that matters. What are we doing? Now, up to this point, I have been showing you averages. So this is 5 runs each on 175 nodes, average there. Okay? There's the actual data. So we have these processors that under a power bound, we were getting different performance. It turns out they give us different performance even if you have just turbo enabled. Each processor has a slightly different amount of thermal overhead. It will spend different amounts of time in these higher frequencies. We end up with an inhomogeneous machine. Let me zoom in on a couple here. The squares and the diamonds are 2 different nodes. Now this is actually worse. I'm showing you the combination of using 2 different processors, and there's still this much variation, and I think, yes. So let's look at the 16 case. This is the most efficient node that I have. What you see is there's almost no variation in terms of power. Okay, that's interesting. there's a significant variation in terms of time. That means if I just run this same benchmark 5 times, I get that much of a distribution in execution times. Now, that's my problem. We're using Linux on this. Linux is notorious for non-deterministic performance, and I can talk at great length about that if anyone's interested. But that's a problem that's a Livermore problem, not an Intel problem. The Intel problem, up there is the least efficient processor. Again, or least efficient node. Within the node, you're getting the same power draw, very little variation there, about the same amount, roughly, of variation in execution time, but this node runs significantly slower all the time and uses more power to do it. Why did we buy that node? So I suggested to Intel that maybe what we ought to do when we buy the next 10,000 processors from them is just grab a couple of interns and have them test each of these processors and send back the bottom 95%. And Intel didn't like this idea very much at all. This is a binning problem. When Intel is writing these processors onto the die and stamping them out, they know that the performance is going to be varying. How they've handled this thus far is they have 5, 6, maybe a dozen bins. They test the processor, see how hard they can push it before it starts failing, and put it into that bin. So the better the processor, the fewer there are of them, the more they charge. If we're in a situation, and so what we're seeing is within one bin, there's this much variation. If Intel liked, and they don't, they could chop these bins up much more finely, and this variation would go down. They're not going to do that. We're not sure what's going to happen. We may just say, look, we want the absolute best processors, or if we're not getting the absolute best, give us a much narrower range so we don't have to think about this problem. Or maybe we develop the software tools that allow us to handle this, and we buy cheaper processors. Don't know yet. So far I've shown you variation within a single processor, variation on a node. Now I want to talk about the problems we're going to be looking at a job. I'm running a simulation. I've got so many processors. I have a job power bound. How many nodes do I ask for? How many cores per node do I use? I don't get into it here, but do I turn on hyperthreading? Do I turn on turbo mode? This is a data set from Tapasya Patki, another PhD student I work with. This graph shows SP, which is computational fluid dynamics core. We want to run a particular problem with a 4,500 watt power bound for the processors. And she went through and explored the entire configuration space. What we have is a set of power bounds, starting with 51 watts, going up to 115 watts. Cores going evenly up from 4 to 16. I think I fixed the nodes on this. It's starting from 8, going up to 32, I think. Someone can count that if they like. You pick a power bound. You pick how many cores per node you use. That partially constrains how many nodes that you can bring up. That determines how long it takes and how much power you used. The point out here is the 4,500 watt power band. All of these configurations came in at or below the power bound. Okay? And there are worse configurations that do this. We're starting off from sensible, the red line. If you were to run this now, what you would probably do is give the processor all the power it wants. Makes sense? Use all of the cores. That's a reasonable place to start. That constrains how many nodes you can bring up. You run that fast, and you don't even use all of the power that you were given. Let me take this moment to emphasize again. I am not trying to save energy here. I'm not trying to save power. We have been given a power budget. I'm trying to use all of the power to run as fast as we can. Now, if it turns out that I can run equally fast using a less amount of power, we've bought the wrong machine, basically. If you go through and just manually search for the optimal configuration, it turns out a modest power bound, just drop 10 watts, drop off 2 cores. That combination allows you to bring up a lot more nodes. Because you have more nodes, you have more memory bandwidth in total. This benchmark likes more memory bandwidth. You end up running twice as fast, and you use up all of your power. It's very unusual to have a paper in systems where you can say, do this, you'll run twice as fast. So we were really quite proud of this. And that's not just SP. We see these all over the place. We do not have a good idea of, we do not have a model that allows us to predict what the best configuration is. Finishing up. We've looked at processors, we've looked at nodes, we've looked at a job. We would like our developers to write code where every processor is doing pretty much the same thing. It takes the same amount of time. They all communicate at exactly the same time, and then they do it again. In the real world, this never happens. Here is a cartoon representation of a job. You have processors, or nodes, if you like, going on the y-axis. You have time going along the x-axis. And what you see is this node does this amount of work. At that point, it sends messages to its 2 neighbors, and usually this is more like 10 neighbors or 30 neighbors, but that's hard to draw, so here it's going to be 2. And then it is stuck until it receives messages from its neighbors, at which point it can go on and do some more work. If all of these lines were identical, my life is a lot easier, okay? What we have, though, is this kind of load imbalance where the red line is the critical path through this directed acyclic graph. All that means is nothing along this path blocked. If you want to speed up this application, you have to make execution time smaller on this red line, at least until it generates another red line. If you make anything on this red line run slower, your whole application slows down. If you are off the critical path, you have spent some amount of time blocking. If you're blocking, you are just hanging out, burning power. No useful work is getting done. So what we would like to do is slow all of this computation down to the point where it meets the critical path. If you lower the clock frequency, you run slower. That also lets you cut the power down. That means we can dump some more power onto this critical path, and this looks like a really interesting control problem. How do you make this run as fast as possible, given a power bound? How do you discover where this critical path is as the program is running, and dump more power to it and take power away from everything else? That's just within one job. Of course, we have lots of jobs running on this machine. Now you have yet another problem of, if I'm the scheduler, I used to be able to get away with saying, okay, you're a job, here are your nodes, you can run for this amount of time, go. Now I have to say, and here is your power bound. How do I determine what the power bound is for each of these jobs? When one of these jobs finishes, I've got nodes freed up and I've got power freed up. Is the best thing for throughput to dump that power onto an already running job, speed that up a bit? If a high priority job comes into the queue, that's going to go as soon as it can. Should I pull power from already running jobs and stick that power into the high priority job? We don't know how to write this yet. That's somebody else's dissertation, and I'm happy to advise that it's a really hard problem. So, going down to the processor, coming up through the node, coming up to the job configuration, to the runtime system, to the scheduler, this entire software stack is going to have to be rewritten to deal with a power bound. Ultimately, that lets us get more science done for the machines that we have. That's what I do. And coming back to that, this is a different way of thinking about computing. I don't know of any other field where you have a power bound and you're trying to push through as much computation as you can. And with that, I'm looking for interns. So thank you very much. Happy to take questions. Yeah. Go ahead. Yeah.
Where do we apply?
Send me an email, rountree@llnl.gov. Quiet group. It's okay. I don't bite until I hire you. Yeah.
You had mentioned when there were 13 cores that the speed slowed down significantly. Is that a similar principle to when you have two RAM slots, you put 4 in one slot and then 1 in the other? Just sort of odd number becomes.
That's an interesting question. Actually, so do you know why it slows down when you do that to RAM?
I know it has something to do with the 2, 4, 8, 16.
Yeah, my best guess is that if you have balanced computation, you will get the speed up you expect. And if it's imbalanced, you're waiting for that one. What bothers me is I would expect you would just not run any faster. If you go from 12 to 13, I can see running at the speed that you've got at 12, but here you're running much worse than that. Is it trashing the cache? Is it, I don't know. I'll find out. I'll pay. Okay. Yeah.
In the graph where you had the number of cores and the y-axis was time, or was
frequency,
power consumption, and then the x-axis was time.
There were a few of those, so
for that one, yeah.
Oh, okay.
So why wouldn't you just stick with 14 cores?
We would love to stick with 14 cores. The problem is we don't know how to predict this job would run best at 14 cores. If we were doing apps, it's easy enough to test every possibility because cell phones are cheap. If you're taking up a $100 million supercomputer, it's hard to justify, yeah, I want to run this 30 times to find out the best configuration, and I'm never going to run this input deck again. So, yeah, in this world, you may be in the queue for a month waiting for your job to run. It goes, and then you find out as the job is running what the best configuration is, and you've got a very large search space. And by the way, don't screw up the job because then you'll be in the queue, another month. That's why this is hard. Yeah.
What's the leading idea for why the variation in processor speed is that a semiconductor device physics problem?
Yeah, okay, I'm not a physicist, I'm not a hardware architect. This is my understanding of what's going on. When you're growing that silicon crystal that you're going to be writing on, there are impurities in it. And if the impurities are bad enough, it doesn't work. But if you're getting down to the actual transistors, some transistors, because of those impurities, are going to need a few more microvolts or whatever to push a bit through. And so what the effect here is just that sum of those impurities in the silicon that this particular processor happened to be made out of. It's a known issue that if you are at the edge of the die, you get a different performance or a different set of impurities than if you're at the center of the die. I think because the universe is this way, the center you have much fewer impurities. But that area is also much lower, therefore that's why those processes are more rare. And if anyone would like to contradict that with a better answer, I'd be happy to hear it. That's, yeah.
Other questions? No, thank you again.
Thank you.